So here is the outline of the talk. So first we're going to talk about the origin of optimal transport or discrete density matrices, quantum optimal transport, semi-definite programming, and quantum optimal transport is cheaper than optimal transport, the swap operation, properties of the quantum optimal transport, Wasser side to distance, SWAP-fidelity and related questions, and metric and projective space. So I hope I cover everything, and if not, then I think you have it would be online. Okay, next. Okay, so what is the classical optimal transport? So this is initiated by, I think it was Monge, but Monge for sure. And so we are going to fast forward to 1941, when actually before that, Kantorovich. So they stated this problem for, let's say, in much more discrete version, in much more, let's say, specific way. Suppose you have M factors producing just one product G, think about Soviet Union, and you distribute to N customers. And you want to do it in the best way, minimal cost. So P1A, P is a density, it's a probability, and so P1A means let's say this how much factory 1 produces, let's think about like shoes. And PB is how much of this production let's say the store number 1 gets, okay? And so this is distribution of capacities of factors and customers. And Aij would be, it is a proportion of, let's say, of this product from factory Ai to the store number J, okay? So this is essentially Aij, what we saw, it's a joint distribution or coupling of 2 random variables. So if you sum on the rows of A, you're going to be this distribution PA, and sum on columns, and you're going to do the distribution PB. Okay? So, and let's call this one gamma classical. It's all possible coupling of 2 given probability vectors. And you observe that this is not non-empty because this matrix PA, all my vectors are column vectors, PBT are in this classical. Okay, next. Okay, next. Okay, so the cost is Cij. This is how much it costs to transport from factory I to store J. And the cost of total transport, it would be this sum. And it would be just, if you take C transpose A, would be trace of this matrix. So the classical optimal transport, the way it was stated by Kantorovich, it was that this is the minimum of this, let's say, all possible coupling in such a way that this would be minimum cost. Okay, so this is a linear programming problem. So we all know as theoretical mathematicians that actually now it's a polynomial time computable. But when you do explicit computation, if you want to do it, it's important to do it fast. So this would be the topic of, I think, workshop number 3, so which I hopefully would participate to. And so what are the reliable algorithms? Now, in linear programming, a very useful is a dual maximum problem. You can restate instead of the minimum maximum, it would be like that maximum of X transpose PA plus Y transpose PB. So this is going to be now 2 numbers. When this rank 2 matrix is less equal entry-wise than C. Okay, so this is a dual problem. Next, okay, so the reason it's, the reason this linear programming whatever important is what happens if you want to compare 2 different distributions. So this is a very practical problem. It means appears in many areas. Okay, I don't know about AI, but probably it's there. But for sure, like if you want, let's say, compare pictures or something, this is good. So what you want to do is you assume that n, and now you have that m and n are the same, and you are given this matrix Cij, which is a distant matrix. What does it mean? You have n from 1 up to n object, and the distance between I and j is Cij. So you want this C to be a symmetric matrix, Cij, Cji. You want Ci to be 0 because you want the distance between I itself is 0. And you want Cij to be positive, the distance between two I different from j. But you also need to satisfy the triangle inequality. You want to do the triangle inequality. So if you have cost like that, then one can show that this TCPA is a distance on pi n. And the Wasserstein distance, which is Wasserstein introduced some time ago, it is, so he introduced it, of course, continuous version of that, and we are now just doing like that. This would be distance for any t greater than 1. So for t equals 1, just would be the optimal transport, would be a distance if this C could satisfy this inequality. Okay, next. Any questions here? Okay, no, okay. Next, so now if you don't have a distance, what about semi-distance? Okay, then the semi-distance for C, it would be just this condition that Cii is 0 and Cij equals Cgi, symmetricity and positive. Now then you can show that this TCPA is greater or equal 0, it would be, and if equality holds, this would be 0 if and only if PAPB. But then you don't demand that it satisfies triangle inequality. Okay? And this is the reason why it is true. So, but let's continue. Okay, so now, so the last thing before we're going to quantum mechanics or quantum, we see so there is something what's called a Bhattacharya coefficient and Hellinger distance. So what is Bhattacharya coefficient? So suppose you have two probability vectors, and then the Bhattacharya coefficient as follows. This would be, you take sum of square root of pi, square root of qi, because this is a probability, so they're non-negative. You sum them and take square. Now, so this is always non-negative. And so this FPQ, if you take a Cauchy-Schwarz inequality, would be less equal than P1, Q1, and P1 means the sum of absolute values of Pi or Qi, but it's sum of Pi because they're non-negative. So it's one norm. So FPQ is 1, would be maximum 1 if and only if P equals Q. Now, Bhattacharya distance is something like that. Well, it's exactly like that. But we are not going to use it, but there is a Hellinger distance. If you take 1 square root of minus FPQ, which essentially would be the two norm of this, difference of these two square roots, okay, of the vectors, square root of 2. Well, this is a norm, therefore you see right away it's a distance. So this is Hellinger distance. So the next thing that we are going to do is we are going to talk about states and density matrices. So what is the difference between classical probability and quantum mechanics? So it is as follows. So when we take a vector in CM, so it's a column vector with complex, let's say, coordinates, then it's norm, which means two norm here. Sum of the absolute value xi square root, it's equals 1, because each square is like probability, and so this is condition. Furthermore, if you multiply x by a phase by e to the power I fifth is real, or by a zeta complex number of complex value 1, this is the same state. It's not the same vector, it's the same. So therefore, essentially, this, the way I said it, it would be, we'll talk about it later, would be points in the complex projective space. Okay, now, denote by HM the set of Hermitian matrices. So everybody knows what Hermitian matrix is, right? So I don't have to say it. And now, on these Hermitian matrices, we are talking about HM pluses would be kind of positive semi-definite matrices. And density matrix is just all positive semi-definite matrices whose trace is 1. So this is the analog of the probability space, but it's non-commutative. And then if you take f rho sigma defined like that, so remember, if FA is a positive semi-definite matrix, there is a unique matrix which is square root of that. Okay? And so then if you do something like that, if you never saw it, don't worry about it. But it is the exact analog of the of the Bhattacharya, let's say, constant, and it's called Uhlmann Jozsa. Well, this is probably a Hungarian name, but so it's probably Jozsa, but in American it's probably Jozsa, fidelity on density matrices. And if you take this square root of f rho sigma is going called root and fidelity distance on density matrices. It demands a proof, but it's true. Now, one of the most important things of quantum mechanics is entanglement, right? So entanglement and let's say was mentioned maybe the first time by Schrödinger, but then it became very famous with a paper by Einstein, Podolsky, and I forget the last name, but doesn't matter. So because this is actually everybody wants entanglement. Einstein didn't believe that. That is not, but the point is that if you look now at citations of Einstein and see what is the most cited paper, is this paper on quantum mechanics, which he was wrong, right? Because he said we believe that there are no hidden variables. But anyway, so how do we do it? Let's say mathematically. So entanglement means that you have to take there are two sides at least, two entanglement. And so you have a tensor product of CM/CN. This is you can identify as a matrix M by N. So if you have, bipartite state is a matrix M by N. And of course, it's sum of the squares, the absolute value must be equals to 1. And when it is unentangled, it is actually a matrix of rank 1. XY, so each one separately. Otherwise, it's called unentangled. Otherwise, entangled. Okay? So now, linear operators. So if we talk about linear operators or bipartite states, well, it would be sort of like the matrices of order M by N. Now, but in order to do it correctly, because we need to take, let's say, we need to trace that there are two sides. So essentially, a linear operator is a 4 tensor, what we call, because there are 4 indices here. Matrix is a 2 tensor because there are 2 indices. And now we have, so you see, we have this I and P. This is from part number 1, and J and Q number 2. And now, remember, when in classical, let's say, coupling, we have to sort of take sums of row on colos. So this is a substitute in quantum mechanics, called by partial trace. So first of all, you can see T as either Bloch matrix with each matrix is M by N. And this one is then, so you can, or you can see Bloch matrix with each matrix is tau jk, and this is a matrix M by M. So okay, so it's partial trace means that you have to think about 2 sides. Let's say Alice and Bob, and each one has a particle, but it's entangled. So you want to know actually what is the particle that Alice has, without forgetting about what's Bob. So there you trace, okay, so you trace Bib, you trace Bob. So what does it mean? You sum on the indices J and J here, and leave it like that. You're going to, and then it would correspond to sum of the diagonal blocks on the matrix, okay? And trace A is similar, and total trace, you takes first trace AT, trace, and trace. So this is a total trace. So this is a sort of the analog of tracing out, let's say, of coupling probabilities. Okay, so what's a bipartite density matrix? Well, it's just a matrix m by n with non-negative trace 1. Now, if you take trace out of Alice, you are going to get a smaller matrix, and this is sort of the matrix that Bob holds, and the other one is what the Alice holds. And coupling would be the set of all bipartite density matrices, such that when you trace Bob, you're going to get what Alice has, and the trace Alice, and you're to what Bob has. Okay. Again, this is non-empty because you have the row A tensor row B is going to be in this set. Now, gamma Q RB is exactly this only one if minimum rank row A rank B is 1. Okay? So when the question is, well, it's just when gamma Q row A, when the coupling contains the rank 1 matrix, and it's easy to show after actually if and only if row A and row B co-spectral, because what it means that each one is a positive semi-definite matrix of rank 1, of trace 1, and then we can take about its eigenvalues, okay? And then cospectral means that they have the same eigenvalues or they are similar by unitary metrics, okay? So if you do, so the claim is, if rho is rank 1, then it must be of the form X tensor X star, because this is the analog of rank 1 matrix. U vector times U star is transposed with bar. Okay, so trace of row A row would be this one. This is going to be, and these two matrices are cospectral with just singular value decomposition for mathematician, or it's called what's his name? Okay, I forgot the name, but it's Schmidt decomposition by physicists. Okay, so why? So you see, if you have the same spectral, if you have the same spectrum for X and Y, then you look at this matrix row, it is going to be in this set. Okay. Now, what happens if we change, let's say, if you take row A and change unitary similarity, this is called, let's say, that's what Alice can do. It's called a local transformation, because that's what Alice do, and the Bob can do the same with V. So this just means that Alice and Bob just choose sort of references. Like if in order to measure, you should take an orthonormal basis. That's what it means. And so then you have this identity. You have that it is the same. Well, it's like the same. Okay, next. So next thing is what we want to mention is quantum decoherence. So we take a density matrix. It's represented in some orthonormal basis. So this is the Dirac notation. I mean, first I hated it, but now there is some let's say, conciseness in Dirac notation, but sometimes it's not so good. But anyway, so this is EI. So this is what we do, unit vector, 0, 0, and 1 at I, and this is the Dirac notation. So then when you do that, the row is of this form. It's represented by a matrix rho ij, okay? And this matrix is just Hermitian, positive semi-definite, trace 1. Now, if you look at the diagonal of this matrix, is going to be a non-negative definite matrix. All diagonal entries must be non-negative. And trace 1, the sum is 1. So this is probability vector. So every density matrix induces a probability vector on the diagonal. But now if you change the basis, you're going to have a different one. Okay? So if P is a probability vector, you associate with dP is the diagonal matrix with these entries. And now, so what is decoherence? Because when you have a physical system, you know, there are fluctuation and it interacts. And so what happens is decoherence simply says that sort of the off-diagonal element started to die. Okay? So now if you take row A like that and row B like that, and you do let's say, and you do the classical. So you, okay. So let's look at all coupling of two density matrices. Now, if you look at, let's say, if you look at this gamma classical coupling and take diagonal matrix, it's going to be here. So therefore, this set is bigger than this one, or less equal. And now, if you do it like that, if you do for two diagonal matrices, this Bhattacharya quantity is going to be exactly the Uhlmann Jozsa fidelity, and this is going to be this is going to be a distance. It's going to be a Hellinger distance. So we have all analogs for that. Okay. Next. So the next now we are talking. The next step is talking about quantum optimum transport. So what is that? So this is. So let's see. So we have two density matrices, and we have all possible couplings of density matrices. Now we take a C, which is a Hermitian n by n matrix. Now you can assume that C is non-negative definite. I will explain why. And then you take minimum on trace. Now trace of C of rho, it just means that you measure. So C is observable, what we call, and then so you do some measurements with respect to the matrix C. Okay, and you take minimum one. This would be quantum optimum transport. So this is. So you see, we replace the gamma classical with gamma q with this one, and we take the same thing. So it's very similar. And so what would be the explanation? What is sort of physical explanation? Well, all Alice and Bob, they have two particles which are entangled, but you know what's rho A and rho B, but you don't know how they're entangled. And you take with this C, you take C these measurements, and you want to know what is the minimal possible outcome. That would be the quantum optimum transport. Well, okay. So now the point is things that, you know, in mathematics or in physics, you can define all kinds of wonderful quantities. But hey, but you want to compute it, you want to do experiment. If there are many particles, let's say think about quantum computers that you want to build, then everything becomes very big, and the computers is just impossible. So we need to do something in quantum mechanics, something which is computable. And unfortunately, let's say this problem as it's stated is essentially follows to the semi-definite programming. I hope that everybody heard about semi-definite programming. So, and the good thing about semi-definite programming that it's computable polynomially with precision epsilon. So you want to up to epsilon. This is the difference between, let's say, linear programming. And so then it's computable if you mean with input and precision up to log, it's polynomial log epsilon. Okay, so if you fix this C and you look at quantum optimum transport, actually this would be a continuous convex function. Okay, so it's convex is quite easy because you just sort of, you know, when you combine correctly, it's from the minimum, and the continuity is a little bit more tricky, but not much. Okay, also if you take rho A and B, and this one contains rho A and rho B, so therefore, because its minimum is less equal than 1. And you have this, you know, relations that what if you do if you change it locally. Okay. So now the next thing is what you see, what you say, it's quantum optimum transport is cheaper. It means it's less. So what do you assume? Okay, you assume that rho A is a diagonal matrix, and rho B is also a diagonal matrix, diagonal probability vector. This is classical. And now you take minimum of that, and then this, if you translate it to the, let's say, only to the diagonal elements, then you're going to get actually classical linear transport with some matrix C prime, which is a diagonal of C, and then And then you can show, and this is obvious, this is equality. But so this was the first time, was noted by Cagliotti and Gauss and Paul in 2020. But actually, how small you can go? So in the joint paper of Cole, Eckstein, myself, and Zhechkovsky, we show that, very simple example on qubits. Qubits are when n equals 2. This is, let's say, like photons. And you can be 1/7 of the thing. So next, okay. So now the next thing is a dual formulation. So again, if you want to do study and do some properties, you always have to know what is a dual formulation. So in SDP, the dual formulation is you have to replace minimum or infimum by supremum, okay? That's what here. And what is now the condition? So you want a supremum of trace of sigma A rho A, sigma B rho B. So sigma A and sigma B are from Hn. So you see it's actually much more smaller than to do it on n by n matrices. So it zooms out. So this is good problem for computation. But there is, of course, a payback. So here you have to satisfy this inequality. When this inequality means that C minus this part is positive semi-definite, okay? So if rho A and rho B are positive definite, then supremum achieved. It's just Slater's lemma, what we say. But if not, then you can have an example which is the supremum is not that the supremum is not achieved. Next, okay. So the next thing is what is a swap operator? So again, we are just now looking for bipartite states. Okay, so this is the first state Alice is in a Hilbert space number 1, let's say Cm, and the second one Hilbert space Cn to 1. And so swapping is just what it says. You just sort of swap between between Alice and Bob. Okay, so this means that if you have X, if you think about let's say the states here bipartite, those are matrices, and so X tensor Y is just X times Y transposed. Okay, no bar, Y transposed, and so then you just sweep the two sweep factors. So if you do it on matrices, then this transformation of matrices take a matrix to go to its transpose. Okay, well, so now we're interested with the case most that we have that the M and N are the same Hilbert space. So then, then X transposed, when you take again transpose is X, so it means that this is involution is also self-adjoint operator. Now, when you take n by n matrices, it naturally decomposes to, let's say, every matrix is the sum of symmetric and skew-symmetric matrix. I think here maybe it can do so. If you have a matrix X, which is a square matrix, so it's of the form X plus X transpose divided by 2 plus X minus X transpose divided by 2. Okay? So this matrix is symmetric, and this is what we call antisymmetric. So antisymmetric in this would be corresponds to fermions, and the symmetric ones would correspond to bosons, but it's only provided is D equals 2 bipartite, but you can do it more than D, okay? So this is the composition that that we have. So if you take the set of all symmetric matrices is like that. The set of all skew symmetrics, it's this one, and this is direct sum. And if you take the standard inner product in the space of, let's say, n by n matrices, x, y would be trace of x star y. These are going to be two orthogonal spaces, and therefore, the eigenspace, and therefore the eigenspace corresponding to S is those, the symmetric ones is with, because when you take symmetric and you take its transpose, it's still symmetric, the same one, but if you take skew symmetric times transpose in -1, it corresponds to the eigenvalues plus -1, okay? And you have this, so you have this one, you can see, the point is when you want to preserve the, the swap with two local operation, it's not so simple, then here you take, from this side you have to take U star with star, but here is the U, so this is not going to preserve identity. Okay? If you take the trace of S row area tensor B, it's just trace of row area 2. I think it's called Vermeer's formula. And if you take transpose of Q or B, you're just going to transpose this one. Okay? Next. Okay. So now we are going to introduce this operator CQ, which is I, identity minus S divided by 2. It's actually orthogonal projection on all skew symmetric matrices. And now you take the optimal transport, which is paired to CQ. And so then, it's easy to show that this is non-negative. Why? Because C is a projection, so it's non-negative definite, and you take it and you trace and you multiply by non-negative definite matrix, then the trace of that is always non-negative. So you have this one. Okay, what's happened? Okay, this one. Now you can show, it's not so difficult, that the equality holds if and only if row 1 and row 2. And now, because of the previous property, when you take S, you can sweep it so it would be also symmetric. So now the question is, you want a distance. You want an analog of the Wasserstein distance. And now here is what happens is, you say, okay, first of all, this is not going to be a distance if P is between 1 and 2. You do just locally and show, no, it won't be a distance. However, if you take P equals 2, we conjecture that it's a distance. And when I started to prepare this lecture again, this paper that we wrote was maybe like 3 years ago, and my memory is not so good. I do some other stuff, so I have to refresh me. So for P equals 2, for P equals 2 and qubits n equals 2, it is a distance. But we can show it for other cases. We do numerical simulation, and it seems that we don't have a counterexample. So we conjecture the distance. So we'll see that this distance is sort of sandwiches between two classical distances. So again, why it's important to have a distance? Well, because you want somehow to compare, let's say, you want to compare row A and row B, how far they are apart. So if you want semi-distance, so TQ is already good enough. If you want distance, we hope this half enough. But actually, we show that it's all, I'll show you, yes, I have to show you that you can milk a distance from there. So maybe it's not so important. Mathematically challenging. So if you really want a challenge, try to prove it for, let's say, even for n equals 3. I was trying, but hey, it became too complicated. But you can look at let's say, this paper of Kohl, Eckstein, myself, and Zizkowski. The references are in the last. Okay, next. So this is how you prove that this is semi-distant property. So you do like that. So if they are the same, if you have row 1 equals to row 2, and this is the decomposition, this gamma q row B, this is a symmetric tensor, and therefore the trace CQ is on skew symmetric, therefore it's 0, but it's always greater than 0. This and other direction, you show it. Okay. So next, I don't want to go to details because when I'm looking at, let's say, listening to some other people's lecture, and it's hard to follow, details and the let's say, and the notation. So another one. So let's do some property. First of all, the quantum optimum transform with respect to this swap or this operational projection on the skew-symmetric matrix is less equal than this one. Because you just take row 1, row 2, tensor row 2, and this is the minimum. Now, if minimum rank is 1, this gamma q, this is it. And therefore, it's equal. So you can do like that. You see, if you wonder like that, so you can, if you have two like that, so you can, it would be the same if you change, if you do the local operation on A and B, but they must be the same local operations. You cannot do this. Now, if you take U to be equals diagonal plus minus 2 in average, because it is convex, then you have this inequality. In other words, if you have an optimum transport between two density matrices and you study the optimal transport on the, let's say, on the coherence, it's going to go down. Now, in this paper with which I mentioned, that's there is a very close connection between this one and classical one, but it's with a twist. Okay, so now let's say after this analysis that's in this paper, you can show that this is greater or equal than half of maximum U on A on this quantity. Now, if you look at this quantity, this one is very easy to show. That's square root of that. So if you take square root of this quantity, it would be you forget about this one, that this is going to be a metric. Okay? So, and for n equals 2, its equality holds. And if you want to prove this one, you need to use this inequality and use duality and 4, which those 4 is here. Okay. Next. Okay. So let's talk about the distance induced by that. So the conjecture is that this is a distance, but we don't know how to prove it. But as I said, but if you look at this this maximum U about this one, if you think carefully, this means that this quantity is greater or equal than this one. So square root of row A, remember that square root of row A is a positive semi-definite matrix, and although this one, and this is a norm, so it is a norm, what's called a Frobenius norm, which means okay, the norm here. Okay, so maybe just since I said maybe so, the Frobenius norm, let's say of X is square root of trace of X star X. In other words, it's just is a standard L2 norm, and this is the inner product that I said. Okay. So once you know that, then essentially, so we call something a weak distance if it's semi-distance and majorize the distance, and then it's easy to show that it always induces. This one induces a true distance with, let's say, which is the biggest distance that majorizes this one, and this by this formula. And so we call this Wasserstein 2 distance. And of course, this is a mess. How you compute that? But okay, so we conjecture that this is the same like this one. Okay, but we don't know how it's true. But anyways, let's go next. Oh, oops. Okay, so I need to do something here. Okay. So next. Okay, next is again, we're going to swap fidelity and related quantities. So if you have any matrix ACN, there is a way from this matrix to obtain positive semi-definite matrix, and this is A star, and take square root of that. Okay? So if this Frobenius norm is 1, then this is going to be a density matrix. So fidelity of f rho b, so this is exactly the same as Uhlmann Jozsa fidelities is this one. Now it's square root of rho b. This is not a Hermitian matrix, so you take this one and take this one square. And then you can show that this gives you, if you take square root of that times this one, like in the, let's say, in the case of scalar case of probability, this is going to be a distance. This is called the Beer's distance in quantum mechanics. There is also another distance, infidelity distance, and one is measured by the other one. So swap fidelity, we are going to take a max trace S of rho about all this one. And this is exactly, it's going to be equals to that one. And so we have this nice inequality that swap density, swap fidelity is greater or equal than standard fidelity, Uhlmann Jozsa fidelity, but less equal than square root of that. And equality holds if and only if on the left-hand side, not infinitely, well, if minimum is 1. And we have here, it's called what we say super multiplicativity. If you have rho or rho b, and then you take multi-tensor with c into this. So in other words, now you have, this is 4 partite, and you take this is greater or equal than that. Okay.
S here.
Sure. Go ahead.
Is the projection again projection onto the antisymmetric lines, where is it?
No, can you repeat, Dima?
What is S in the
S is the swap. S is the swap.
It's the projection onto the.
No, the project. No. Okay, so this is. I need to answer this question. So let's do like that. Okay, so S of, let's say, X and Y, this is equals to Y, X. Okay? That's the swap. The swap is that you change. And the Q was half of I minus S, and this was the projection. Okay?
I'm sorry, so I got confused. So F is then not the distance, F is just the
fidelity. F is fidelity, and Fs is fidelity that we introduce with respect to swap. So this one, it's actually 1 is minus 2 quantum multiple swap. Okay, now it's clear? Okay, thank you. Okay, so here is a sort of the, say it again?
So the swap acts on both sides of rho?
Oh, no. When on rho itself?
Yeah.
No, just on one. See, S is a swap, so it acts on the CMN or the bipartite states, right? And then S, when you multiply by rho, acts only from one side. If you, let me answer this question. You have S rho, and you take trace of that. And you have, if you take S rho S, then essentially you just changes this one with, so if you S rho A equals, rho equals so S rho, it means then it would be, so what I show that S gamma Q of rho A.
S rho is not the motion, but it's not the distance it's computing. It's computing fidelity.
So let's see. Then I first of all write it. S is equals gamma Q rho B rho A. So does it answer? So you have, if you act it on both sides, and you have this one bipartite, it just would be something in bipartite here. But here, when you take trace, no, you act only from one side, because trace of S rho S, you can trace, you put it here, S squared is equals 1. Okay, clear?
Yes.
Okay, fine. So this is sort of, let's say, from our paper in physical review letter. So suppose you have here, I think one of them is, this is a Beer distance. The other ones, I think it's root infidelity distance. And this is for qubits. And this is let's say, the Wasserstein Wasserstein distance, which is actually square root of TQ for this for qubits. And you see, it's all this 1 hour is sandwiched between these two ones. Okay, so it's okay. So you know, it's another metric. Okay, and this is exactly what you see. The picture is okay. So let's see. Okay, so let's see. So I have a say 2 minutes or something like that. 5 minutes. Oh, eternity. Okay, okay. Thank you. So CQ is identity operators on A. But now so what is a basis on A? So what is a basis in, let's say, fermions? Okay, so if you want to do mathematician, it's a wedge product if I is J. It corresponds to a skew-symmetric matrix, which has only, let's say, 1 on ij and -1 on ji, and divided by 1 square root of 2 because you want trace 1, okay? So now you say, now I want to be not this CQ would be if you put all lambda ij equals 1, except I is 0, it doesn't matter. So you want a little bit more general metric, okay? So how about, let's say, putting, so you can consider square root of 2 TQ square, and so this would be, is that a metric? Okay, so if this is a metric, we have to have that lambda ij is a distance metric that I talked about. This is necessary condition, very easy to show. Again, sorry. Okay. Okay, good. Okay, let's see. So then, so here is I showed y, but it's you know, we can go through that, but it's easy. You just choose ei, and ej, and you get that this is lambda ij, and you have triangle inequality. But the question is this a distance on the all density matrices? And we showed, let's say Sam Cole, who did the numerical experiment, shows that no, it's not always on density matrices. Even for n equals 3, so it's true qubits or 3 qubits or q-treats. So, but then how about, is that a distance matrix on pure states? So pure states are, it's, okay, so everybody know what's pure state, but if not, then pure state is, the matrix X is X vector X star. So this would be, this is a density matrix, assumes that the norm of X, norm 2, is equals 1. And now you see if you multiply by a phase here, so if you multiply X by a phase, it's from here, it's going to be, it will be the same one, okay? So that's a pure state. So in other words, it's density matrix, which has only one eigenvalue, 1, or other zeros, if you want like that. So we worked hard, and we showed that if, we showed that if, so we say, suppose we say, so let's, so we say, suppose lambda, metric lambda ij on 1 up to n is induced by LP, okay, LP. If you have n vector in LP such that lambda is distance LP. So every distance is reduced by L infinity, it's small proof. But what we showed here in this paper, later paper, this is Bistron, Eckstein, myself, and Miller and Zhechkovsky, that if this matrix, if the lambda ij induced by L2 matrix, then it is a metric. Okay, and so we use a result of Schoenberg. I don't want to get into size. So now we have open problems. If this is, what happens if this matrix is by L1? Or what happens if this is it a metric if lambda is by Hamming distance? So for d equals 2 and 3, we know its answer. But now Thomas Miller proved this conjecture, and actually he discussed also one way also to show the generalized distribution in physics. It means that vectors whose sum is 1, but not all pi's are positive, non-negative. So this is very nice. Okay, so I think this is it. Now, okay, how much time? Okay, so one thing. So you can try to do it to bipartite states, and this very easy to do it, and this is as a measure. So bipartite state is like that. You just take the product, and you can do optimal transport as before. You can do the swap as before, and you can do like that, and so you can define the equidistance, and you can generalize to distance to bipartite, and this is the papers that I have. Okay, so.